Hello brick sculptors and welcome back to Brick Sculpt. Today I want to talk to you about attaching Lego at angles. Now in the past I've always just used the method of taking a plate or a brick and putting a couple studs on the bottom and just kind of using it like a compass and finding a spot where it seems to fit and sticking it down. Now I want to take a more mathematical approach and see if this is actually accurate or if the fit is just okay, and then it would technically be an illegal building technique. So let's go ahead and do some math here and see if we can figure out a better system for determining what angles will work with Lego studs. Now, in doing research on this, the first thing I came across was the Pythagorean triple. The Pythagorean triple is a concept that says you can have one right angle in a triangle, which is important because in Lego everything is at right angles, and you can have three sides that are all whole numbers. So the best example of that is something called a 3, 4, 5 triangle, and this is a really commonly known thing where if you have a triangle with sides 3, 4, and 5, they'll have one right angle and they will all work together. So I figured let's try it. And first thing I did is I grabbed some bricks. Here's a 4 long. If I put a 2 long here, now we have 3 and 4. And I used medium nougat because I have these in 5 longs. So I figured this should stick right here, right? Well, it doesn't. So what the heck is going on? This is math, right? Math is always supposed to be correct. It's not supposed to have any hiccups. It's factual. So I said, well, maybe I should give up on this. But then I looked deeper. I said, wait a minute. This isn't a 3, 4, 5 triangle because I'm measuring studs. And we shouldn't be measuring studs. We need to be measuring length. For example, when you count, you start at 0. You might not say 0, but you're going to start at 0, and you're going to count 0 to 1, 1 to 2, 2 to 3. If I count studs, I'm just counting 1, 2, 3. But really, this is only 2 line segments, 1, 2. So to make this true, I need to add 1 stud to each, and I'm really counting the intervals in between the studs as a unit of measure, not the studs themselves. Let me show you a better example. So if I increase the distance on these arms, and here's 4 studs, putting 1 more at the bottom makes it 5, and 4 across, now we have a 3 and a 4. And the way we would count that is 1, 2, 3, 1, 2, 3, 4. So in theory, if I have a 5 long, which is really 6 studs, that should fit perfectly. And what do you know? It does. Awesome. So it actually worked. Our 3, 4, 5 worked. But we can also scale this up. In theory, if a 3, 4, 5 works, double that should work as well. A 6, 8, 10. A 9, 12, 15. A 12, 16, 20. A 15, 20, 25. And this goes on infinitely. Now, for sake of Lego, let's say we're not building at a massive scale. We're probably not going to go too much bigger than this. But in theory, this should work at really any size as long as we keep these same proportions. And over here you can see on your typical 3, 4, 5 triangle, this is the angles. So you have a 90-degree angle, 36.87 degree angle, and a 53.13 degree angle. And just like any triangle, when you add the 3 of these together, you get 180 degrees. So let's go ahead and try it at a bigger scale. So as I already showed you, here's our 3, 4, 5. If we scale it up and double it, this is our 6, 8, 10. And keep in mind, we have to add 1 stud to each. So this is actually 7 long, 9 long, and 11 long, but we're counting the intervals in between as the distance, not the number of studs. We can scale it up again and make a 9, 12, 15, which in studs is going to be a 10, 13, 16. which makes for a nice round number because you don't have an odd number here. And we can even scale it up again and make for a 12, 16, 20, which in studs, 13, 17, 21. And you could go on forever as long as you keep that same ratio. And the nice thing is if you're trying to support a wall on this, number one, you can put plates under here so they just rest on it. But every one of these triples, you can put a supporting stud. So this is supported in 5 places. So it's actually a very solid connection. This one here has 4 supports. This one here, you can put a support in the middle. So if you're trying to stick down a whole building or the front of a building, you can have a decent amount of attachment and you can put tile in between here. Now, one limitation to this is you're stuck to this angle where you have a 36.87 degree angle up here, a 53.13 degree angle down here, and unfortunately, that's really the only angle that's going to work in this configuration. But there are other Pythagorean triples. So let's go ahead and take a look at another one. Now, unfortunately, a lot of Pythagorean triples out there are going to be really large numbers. But there are 2 that work in smaller numbers. And the reason we need smaller numbers is we typically are going to build Lego on smaller scale. If you had a Pythagorean triple where each of these digits are in the hundreds, it's not going to be very practical in use for Lego model building. But there is one more that works at a smaller scale, and that is the 5, 12, 13 triple. And I can show you an example of that here. So here we have a 5, 12, 13 triple. Now again, we have to add 1 stud to each because we're measuring the intervals, not the studs. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And a 13 length fits perfectly on top. You can also scale that up. I only did 1 scale up here because these are going to get quite large quite fast. But here we have a 10, 24, 26 triple. Now if you were building a really large mock, you could make this even larger. You could do a 15, 36, 39, a 20, 48, 52, and on and on and on. There really is no limit to this. And just like in the last one, unfortunately there's going to be less attachment points because this one side is so long, unlike the 3, 4, 5. You can also put an attachment point in the middle here. So you do have a support in the middle, and you could fill under this with tile. So it is possible. Now, why would you want to use this over the 3, 4, 5? Well, it's a different angle. Your 3, 4, 5 is a much steeper angle. Your 3, 4, 5, 36.8 degrees and 53.13 degrees. Your 5, 12, 13 triple is a 22.6 degree angle by 67.4 by 90. And again, these all equal 180 degrees. So if you want a less of an angle, you could do this method, or more of an angle, you could do this method. Well, now that we know about these 2 Pythagorean triples that work really well with Lego, your next thought is probably, well, what about a 45 degree angle? One where you can perfectly cut a corner, meaning 90 degrees by 45 by 45. Well, unfortunately for us, a 90 degree by 45 by 45 is not a Pythagorean triple. That kind of triangle has a different name. That kind of triangle is called an isosceles triangle. An isosceles triangle is defined by a right triangle with 2 equal sides, which would give it 90 degrees, 45, and 45, and would perfectly cut the corner between 2 straight surfaces. So is this possible in Lego? Well, I did some experimentation to try to find out if I could find a perfect isosceles triangle in Lego, and I believe I have. Now, because I can't measure super precise, I can't say 100% that this is a perfect fit, but I can click these together and I can tell you it's pretty darn close, if not perfect. So maybe you guys know, you could leave it in the comments if you do, if this is an actual legal building technique from Lego. So I believe it is, but like I said, I can't measure precise enough to tell you 100% that it is. In order to find this perfect triangle, we need to use Pythagorean theorem, which I'm sure you guys had learned in school. A squared plus b squared equals c squared, meaning that these two squared added together and taken by the square root equals the long distance. So I did some tinkering around with parts, and I found that a 12, 12, 18 measures out just about perfectly with the Pythagorean theorem. And let me show you an example of that. So I did the first one I did with jumper plates, and I just like the way it fit better. But if we measure this out from the middle of this jumper to the middle of this jumper is 12 studs long. Same thing here. From the middle of this jumper to the middle of this one is 12 studs long. And then an 18 long plate fits perfectly across those. At least I think it's perfectly. Now you might be saying, well, how is that not a Pythagorean triple? And it's confusing, and here's why. Because we're measuring 12, 12, 18 in stud length, and those are whole numbers. But in real measurements, these are not whole numbers. And the reason being is this angle has a different unit than this. So if you look at your intervals, basically you're measuring from here to here to here to here, 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 here. Which this distance, I don't know what it is, but is not equal to this distance. So, though it does work in Lego, and they may have engineered that into the brick, it really is not a Pythagorean triple because these are not equal whole numbers, which means that this one would be a fraction if you were calling this exactly 12. But it does work out perfectly. And you don't have to do it on jumper plates. Next to this one, I laid it out with just studs. So you can see that if I place these at this distance, an 18 long plate fits perfectly. Now you may notice I have a stud in the middle. You'd say, well, why are you measuring at 18 and not 9? Well, there's a reason for that. And I have a jumper in the middle as well. If I measured at 9, it would not be an exact measurement, though it does fit. If you'll notice when I attach this, the 9 actually fits in the half. So that's a half of a stud distance, not a whole. So it does work, and it does give you extra support if you were to attach a wall like this at a 45-degree angle, but it really isn't a whole number. So it does work, but you really have to measure this in 18 long, otherwise you're going to have an uneven number hanging over here. And there are a few that work like that. So 9 works like that. This one here is an example of 13. Now on 13 long, I do have studs all the way in the end. I'm not doing a half stud, but when I go to attach this, this won't fit on an actual stud. It's going to go in the middle of 4 studs. So your attachment is going to look like this, where you have one side on a stud and one side in the 4, and then 13 does fit perfectly across that. I also discovered if you half this and do 6, 6, 9, a 9 long plate does fit, but it does a half. So this one is right on the stud, but this one is hitting this middle piece doing a half stud, although it is a nice secure connection, as long as you don't have to worry about this wall being flush to something. So those are ways you can do right angles there. I think the best one and the most popular used would be this one here, where you do an 18 long and a 12 by 12. But you let me know below. And also let me know below if you think this is an actual legit connection or if it's mildly illegal. Try it on your own. They fit together really smoothly. It does not feel like I'm forcing anything. So I do think this is a legitimate connection. Also, if we want to check it with math, I was able to measure these out, at least fairly accurately, by taking my caliper. So the distance of the 12 long side, if we try to go exactly center on center, is approximately 3.77 inches. It'll be the same thing going this direction. If we measure center on center here, we get approximately 5.33. So if we do the math, it should mean that 3.77 times 3.77 is 14.21. Now we have to add that in our Pythagorean theorem to the same thing, so multiply it by 2. We have 28.42. If we take the square root of 28.42, what do you know? 5.33. So the math, depending on my level of accuracy, the math pretty much checks out. So I think that Lego built this in to the engineering of the brick and that it is a legitimate building technique, but let me know what you think. As always, I hope you guys found this helpful and not too mathematical. If you like this video, please like and subscribe because I'm going to do more like this in the future, and we will see you next time.